this experiments would not have been possible, but this is kind of way outside of my comfort zone. So this is me and Sean like claiming victory in front of the building. Hey, we did it. All right. So buildings can act as cheap virtual battery. Yeah, why is this cheap? And the cheap part is really important. That's the basic motivation behind any of this. Because we don't need an expensive battery. We already have expensive batteries. So what makes it cheap?
Controlling the temperature.
Say it again?
Controlling the temperature.
We're not controlling the temperature. We're controlling the airflow, making sure that we don't change the temperature.
Somehow indirectly.
What makes it cheap is that we are using existing equipment. The building, the HVAC system, all of that is there. We are just putting an extra piece of software and communicating to the building. As long as the building has communication infrastructure, it will work. So this experiment was done. The controller was running in a computer in my lab in the MAEB building. And it was using the UF network to send commands every 40 milliseconds, I think, to the building automation system in Pew Hall. Right? So as long as that infrastructure is there, only thing you are changing is a piece of software. So that's what makes it cheap compared to batteries. Yeah.
Is this currently being implemented?
No, we did it one day and then we wrote a paper and we forgot all about it. We didn't forget about it. Yeah. I'm being facetious. I mean, it's once you prove the technology, we don't do it all the time, because what's the point of doing it all the time, right? It's when utility picks it up, industry picks it up, then you say, okay, now. And then there are other things that have to be done. So if you want to do it, you have to probably provide some sort of incentive to the building, and the contract has to be signed. Okay, I'm going to let you, I'm a building owner, I'm going to let you install this software so you get this service. In return, you have to give me something, right? So this is like a proof of concept demonstration. Any question?
Just to make sure. So you're adjusting the fan speed, you're not turning it on and off?
No, we're not turning it on. On and off is, Sean, did you talk about the TCLs?
Yeah, we started to.
Okay. So yeah, so that also can be done, but that's a separate kind of, because the hardware is different, the control algorithms have to be designed with the hardware limitation in mind. So if you have on-off, that's a whole different problem. It requires a whole different algorithm development. And this never gets turned on or off. You just ramp it up and down. So so this is for one building, and if you can scale this up into all buildings or all the buildings in the US that already have this kind of equipment and this kind of building automation system, how much can we get? We did some back of the envelope type calculations here, looking at square feet and energy use per square feet, etc., and it calculated that with all the existing buildings in the US that already has all the equipment and software in place, equipment and building automation system in place, we can get about 6 gigawatts in this time scale. That's about 70% of the frequency regulation requirement of the whole country. Right? Just by using fans, and not all buildings, okay? Large commercial buildings that have variable speed drives and building automation systems. So actually you can do it like tomorrow. Cost, yeah, this is always the biggest problem. I keep saying it's cheap. It is cheaper, but just because it's software-based solution doesn't mean it's zero cost. I mean, look at Uber. Nothing but an app, but it costs millions and millions of dollars to. I think they're still making losses, right? Yeah.
Their ride business makes money. They lose money on the freight and food delivery.
Oh, is that how it is? Okay. All right. So maybe we need to add like a food delivery portion to this. Oh no, that's actually making the loss. Is the other part is, yeah. So the cost estimate. This is I don't know still how to do this. How do you figure out cost of software development, engineers' time, maintenance because there will be maintenance. So what's going to happen is that something will happen in a building, and if you're a startup, let's say you implement this technology in a building, you'll be the first one who'll get called. Maybe it's because there's a rat in the duct, but they're going to blame you because this is the only new thing happening in the building. All right? So that all of that has to be kind of taken into account in the cost. And Professor Mine has done some net present value analysis for water heaters. We have to do something similar, but I think there's a large part of the cost that's kind of uncertain. And again, potential reduction in equipment lifetime. And these are variable speed drives, these motors. They're meant to vary their speed. But I'm not sure when people who made the motors, what kind of variation that they had in mind. They may not have designed it for this kind of variation. So if I start varying at this range, maybe the motor's lifetime will get reduced, and that is going to add to the cost. And that's something, again, you have to do like a long-term testing to figure out if that's going to happen or not, and we don't know. And of course, the fans are only like 20% or so. Chillers are like 70% probably. And the cooling tower fans are like another 10-15% for the electricity. And the pumps are like 2 to 5%. Kind of ballpark, yeah. So with the chillers, you can actually get much more virtual storage if you know how to control them. And actually it can be done. This is still a research frontier, but we have done some preliminary work. And then the other big research frontier is how do you coordinate many buildings, right? To provide, every building can do a kilowatt scale. Like this guy was able to do about a kilowatt up and down. And it's kind of quite remarkable because the motor is about 7 kilowatt rated, but normally under normal conditions, the baseline conditions, it runs at about 2.5 kilowatts. So we do 1 kilowatt variation over 2.5. That's like what, 40%, and yet no effect in the indoor climate. So what was the point I was trying to make? I forgot. Oh yeah, if you have a gigawatt scale signal coming from the grid and every building, let's say, can do a few kilowatt, you still have to do like thousands of buildings, and they have to coordinate together so that together they track that signal. Did somebody have a question here? Yeah.
Did you have to characterize like every fan of every equipment? Like, was there a constraint?
So that's a good point actually, because to implement this, to design this controller, we had to do this test. And I guess you're right, you have to do this test for every AHU. Now, maybe after like 10 AHUs, you don't need to do any more testing, because then you look at the metadata. You know, this AHU has this kind of airflow, this big a motor, this kind of fan, blah, blah, blah. These are all the possible parameters that can affect this model. And if you have like 10 of these data sets, then you can probably come up with a model for the next building. If you give me the parameters of the building, how big is the motor, you know, what is the nominal airflow, then I can figure out what kind of response I'll get, and I probably don't have to redo this test. But it's a good point. How much, and again, it goes back to the cost of deployment of this technology. How much of the engineer's time is needed before you can get this to work? Yeah. Okay, so coordination, I mean, lots of work has been going on. I guess you're talking about, you have talked about coordination, distributed coordination, or?
Well, yes, I mean, yes, we've talked about, so you'll give a presentation.
Okay, all right. And so Austin is working on an aspect of this problem too. My former student Jonathan Brooks also worked on this. How do you coordinate without like using a centralized controller? Anyways, so this got published in 2015, right? So work was done in like late 2013, and you know how journal papers take forever sometimes. This one did not take too long, but by the time it got published in March 2015. In the meantime, in another corner of the country, something else was happening. Something else was brewing, because a lot of people are interested at this time on solving this type of problem. So there's a group in Los Alamos National Laboratory. Scott Backhouse was the main guy, and he was working with Ian Hiskins, Professor Hiskins at the University of Michigan, and his student, trying to do this sort of thing. A lot of people in the country were trying to do this sort of thing, right? So, and this is what they came up with, because they know about demand response. You guys all know about demand response, right? No? I see some blank faces. You should know demand response by now, right? So demand response has been going on since for decades. Yeah. Okay. Yeah. But it's not. I mean, it's not useless. It was very useful for a different application. It's just people are trying to. It's like trying to push a square hole in a round peg or whatever it is. The other way. I always screw that up, so maybe I should not try that. Anyways, so these guys, because they've been working on like power systems for a long time, so they know about demand response. So they want to say, well, demand response is, something happens, you turn down the power or turn up the power. let's try to do that in this for this application, frequency regulation. So fast. Yeah, so I said virtual energy storage, you can do it many time scales, but for commercial buildings, it's this 1 minute to 10 minute time scale. That's basically the time scale for frequency regulation. And there are a lot of papers on frequency regulation at that time. So they say, well, let's try to do this for frequency regulation. So what their idea was, just like demand response, that they're going to vary the demand by what they call global thermostat set point change. So you have a large building, and they actually did a real test. And that's the problem with this DOE. This was a DOE project. The DOE, they just give you money, jump immediately to an experiment, right? No analysis, no thinking, nothing. They want you to do an experiment and write a report, right? And then move on to the next project. So this is a DOE project. So it's kind of bold to think about what they did. They went to this large building, and there are about 100 VAV units. What they did was they wrote software to remotely change all the temperature set points of all 100 VAV boxes. So every zone has a local controller, that's called a VAV box controller, and you enter the set point, right? So, and the idea was that if you change the set points, right? Suppose you increase the room temperature set point at all the rooms on this building, right? Increase the room temperature means reduce the airflow because that air is cold. So if airflow goes down in the entire building, which means the fan has to slow down. That's how you reduce airflow. The fan slows down, power consumption is going to decrease, vice versa. So that's their actuation. Our actuation was to kind of go in, mess with the software, change the airflow rate command, right? And that takes a little bit more work. Tim Middlecove had to write all this complicated software. They said, no, let's do something simple. Let's just change the set point of all these thermostats, which is easier to implement, right? It's going to blow up in their face, by the way. That's the preview, okay? But they don't believe that actually. They're still fighting us on this. So what happened was that they did that. So this kind of and also because now they don't know what the baseline is. So this is 9 to 11, 2 hours. So you can see that they are trying to do 20 minutes up and down. So they're changing the set points for keeping them for 20 minutes and changing the set points again. And then the power goes up and down. And then they reported, they did that and they got some results. It was not that impressive. Didn't quite work because their paper was mostly like characterization. They could not get this to work the way they wanted. Then they came up with a different story. They realized something after all these experiments, and then they wrote all that in this round trip efficiency paper. And this is what they claim, and this is an experimental result from that paper. They said, look, this is what happens if we try to change this power consumption quickly. So they changed the power consumption by changing the set point. So here, this black line is the commanded power consumption. So this is kind of red line is the baseline. And they want to increase from 160 to 200 kilowatts. And this is 10.5, 11, so that's half an hour. So this is more like 15 minutes and 50. Yeah, okay, so this is half an hour, 15 minutes up, 15 minutes down. And they designed a controller. The controller is very simple. It basically says, okay, if I want to increase power consumption then by this much, I'm going to reduce the temperature set points by these many degrees. That's kind of a mapping they came up with. So they did that, and the first 2 cycles, half cycle look okay. They put this reference, and the blue line is the experimental power data. It's not super great, but it's not too bad. It's working. And then they shut it down here. They go back to baseline, and now look what happens. The power can keep going, and then slowly keeps coming back. It's like terrible tracking, because what you want is you want to go up, down, and then quickly settle down to the baseline. That's what you want. So LNL kind of looked at this and said, this is the extra, this is power. If you integrate over time, you get an energy, and this extra energy is being consumed by the building just so that you can do this power variation. Right? There's an extra energy cost. So they say, well, that's like a battery with a very large round trip, a very low round trip efficiency. You know what round trip efficiency of batteries? So batteries are asymmetrical, electrochemical batteries. So if you bring in 1 kilowatt or 1 unit of energy to charge, let's say you fully charge it. Let's say it's 1 kilowatt hour or 1 unit of So let's say it's 1 unit of energy the battery can hold. So you bring in 1 unit of energy, you fill it up, and then you deliver the energy back. When you try to deliver, you realize you cannot deliver 1 unit. You can only deliver 0.9. Something like that. So that 0.1 gets lost because of thermal dissipation and other things. It's a inefficiency. It's called a round trip efficiency. Pull in, pull back, you lose something in the middle. Yeah.
So before you were talking about they were varying temperature, and now there's a fan power. Were they controlling the fan power, or is that a response to the temperature?
Is a response to the change in temperature set points. Right. So they say, well, look, this is bad because if you try to do this kind of fast, this was their paper, round trip efficiency of fast demand response, that's kind of high frequency commercial air conditioning system, then it's going to lead to this extra energy use, and therefore this is bad. You cannot do this. I mean, that's kind of, yeah.
They didn't talk about any synchronization or anything.
No, well, I mean, that's
got to be it. Like they're turning all the set points up and then turning all of them down.
well, even without any synchronization, even if you like a one giant building with one set point, it'll still happen.
Yeah.
Right, and the reason it will happen is that you have these the time scale is well, there are 2 reasons. One is time scale separation is not there. So what happens is that they did not report the temperature, but I suspect is that when you go up and down, the temperature doesn't come down. At this point, the temperature doesn't come down to 0. In our case, we took care to separate the time scale of this VES with the time scale of the control system, so that when you want to go up and down in the power, temperature basically doesn't change at all. So the climate control doesn't pick that up and doesn't try to correct it. Here I suspect that there was a noticeable response in the temperature. It could be because of the time scale is a bit fast, although it's not that much faster, or it could be that it is like they are becoming super aggressive, their amplitude is very high. So there is a noticeable change in the temperature. Once the temperature went, so how would you get increase in power consumption? You decrease the temperature set point. Make it cold, try to make it colder, then the fan has to supply more power, right? So once you go back, well, maybe the temperature increase in one direction is not the same as temperature decrease in the other direction. So there's some residual temperature away from the baseline. Now the climate control system has to kick in, provide this extra energy to bring the temperature back to baseline. So that's one. The other is, and this is a kind of speculation, is the complexity of climate control system at slower time scale. I'll talk about that in a moment. There is one other reason, non-linearity in the plant, from airflow rate to power, or temperature to power. So I'm not going to go into that. That's a bit complicated. So, but the trick is this whole complexity business, right? So earlier when I showed you all these pictures, I mean, they're kind of all simplifications. The actual system is a lot more complicated. And you don't see this complexity if you work at this high frequency fast, because then the climate control system doesn't react to it. If you start varying at a lower time scale, then the climate control system picks it up and starts reacting, and then everything, all the complexity in the climate control system now kind of becomes visible to you. So what is this complexity I'm talking about? Even for forget about chiller plant or air handling, just the control system that is there to control the climate of a single zone, that already is pretty complicated. And if you look at textbooks on this, you'll see pictures like this. So it says, here's the room temperature, and there are 2 axes. This is the supply air flow rate, and this is the supply air temperature. And the room temperature is in a good range. 60 minutes. So I guess another 20 minutes, 15 minutes. It should not take more than that. This is called a dead band. Okay, if the temperature is in this range, then you just supply some nominal airflow, you're fine. If the room becomes too hot, then you increase the supply airflow rate to make it colder. If the room temperature becomes too cold, you want to heat it, you keep the airflow the same, but then there's a reheat coil. You turn on that coil and you ramp up that heating so that you actually get more heating. And this picture also is not the full picture. Actually what is happening is that this is a hybrid dynamical system. Is that once you have a deadband mode, okay, so there's a typo. This is not heating, this is deadband. In a deadband, it maintains a minimum airflow. Once the temperature crosses this set point and becomes too hot, then the system switches to the cooling mode. In cooling mode, it uses a different PI controller to change the airflow rate to bring the temperature back, right? This is one dynamic system here. And then if the temperature becomes colder, then it transitions back to this mode. If it's too cold, then it transitions to the heating mode. That's another PI controller, okay? The different set of gains, it's another dynamic system. And then to avoid this frequent switching back and forth, there are these dual time conditions. So if it transitions into one mode, it has to spend at least like 10 minutes or 15 minutes before it transitions back. And all of those numbers, all these PI gains, all the dual times, and all these other stuff, safety checks, all of these will depend on the controls engineer who will go into the building and program all this. You have no idea, right, what these numbers are. So, yeah, Naren is laughing because he was working as a controls engineer at some point, building automation sector. So he knows what I'm talking about, right? He's hungry, he's stuck in some corner in Alaska, which is where he was working. And he's like, okay, I'm going to be done with this. I'm going to just put some numbers and get out of here. So you have no idea what this system is. So once you start affecting the climate control, right? So you think changing the temperature set point is going to lead to, change in the fan power and blah, blah, blah. But then depending on how the transitions are taking place, there could be, just because of these dual time conditions, there could be like a 10-minute delay between what you think will happen and what will actually happen. Also may not happen, but also may happen. So I'm not saying that this will never work. The problem is that you would not know when it's not going to work because of all this complexity, right? And that's actually why when we did our experiments, the design, all of this time scale separation, all this body plot business is to kind of avoid that complexity, because if you work in this high frequency range, you never give the climate control system an opportunity to kick in and create all this complexity, right? So the moment you go into the slower time scale, then you have to handle all of that. And the difficulty is that we don't even know what that is, what all of that is, because it depends on what some control engineer programmed into the controller board. So that's actually, it's a slow system, okay? That's the key. But it's a complex dynamic system. So, okay, Los Alamos team wrote this paper. Fortunately, before the paper was published, somehow we got a copy of it. So those of you who are doing research, this is kind of an important point, okay? You need to kind of know people in the field so that any new result comes up, you actually get a copy of the paper before the 2 years it takes for the paper to get published. I think one of us reviewed the paper, or one of the authors kind of sent us, because they knew we were working on it, they sent us a copy. Hey, this is what we observed. And then so wait a second, when we did it, first of all, looked at this temperature set point change, this is not likely to work. And plus, we didn't see any of this. So, but then they were the Los Alamos team, and in fact, I went to Los Alamos to give a talk on this, and they were kind of skeptical. So wait a second, this should happen with your experiments too, right? Because they were quite convinced. So what happened was that because of that, we wrote an ACC paper to present some of the results that we did not bother to present in the journal paper. This also came up in 2015 because all of this was happening in 2014. End of 2014, we quickly wrote the ACC paper, submitted it, and then we showed. So this 40 minutes is where the experiment took place. So see this fan power, there are these slow changes. That's because of the climate control system. Because during the day, there is more heat. It has to increase airflow to keep the building cold. So you have this slow time scale variation, and then in 40 minutes we are doing this fast variation, which is that one, right? But when it comes back, there is no like slow recovery like what happened in Los Alamos, because we are not messing at that slower time scale. So in fact, all of this other stuff that I didn't mention but did not get into, there's quite a bit of work to be done there. Actually, Naren wrote a paper, and it theoretically proved that even at the slower time scales, even considering all these non-linearities, because Los Alamos team was saying that it's because of non-linearities, he actually proved that no, RTE is not small like you were claiming. It's actually, it goes to 1 as time goes to infinity. And it took us forever to get the paper published because the reviewers didn't understand what the heck was going on. Because I say runtime efficiency of HVAC based virtual battery, so that it went to reviewers working in the field of electrochemical batteries, and they have no idea what we are talking about HVAC systems, right? So it took us many rounds of fighting with them. Finally it got published this year.
What do you mean by I know what you mean, but explain what you mean by...
So what happens is that if you look at this, okay, forget about all this time scale complexity I'm talking about. Let's say this is always going to happen, even in our case, right? So what happens is that they did only one cycle. Now the grid is not going to ask you to charge and discharge once and say, okay, stop, you're done. The grid, look at the signal. If you go back to the very beginning, the kind of signals you are asked to track, right? It's going to go up and down all the time. I mean, that's the difference between demand response and this new type of service, which means that you're not going to increase and decrease and stop. You're going to increase, decrease, increase, decrease, increase, decrease. You're going to go on and on. So if you keep doing that, so you'll see this, and then you'll do again increase, decrease, again increase, decrease, and maybe after like 2 days you can say, well, I don't want to do this anymore, just for the sake of argument. Then at the end of 2 days you will expend this extra energy, because by that time also you'll kind of move away from baseline. But I mean, what Naren proved is that this extra is always bounded, no matter how long after you stop. So that you always amount kind of, the extra energy you consume is always going to be finite and small. So as you keep kind of doing this charge discharge, the ratio of that to the total energy service you have provided goes to 0. So the round trip efficiency effectively goes to 1. That's basically what Naren proved. All right. So yeah, their claim is wrong, but they're still kind of fighting us. Not the Los Alamos guys. Scott Backhouse kind of came around to our point of view, but the Michigan group, I think, is still not giving up. They know our papers. I've explained the results, and they kind of, yes, okay. But then they go and write another paper which kind of tries to sweep all this under the rug. So anyways, this I'm not going to go through. Case study is medium frequency. Use the chiller, okay? Now you can get actually much more power consumption variation at a slower time scale. But now you have to mess with the time scale at which the building of climate controller is working. So you have to kind of, only way to make this work is to kind of rip out the climate control system, install a new control system. I don't mean physically rip it out, change the software, so that one control software does both, maintains climate and provides this service. It's like a full redesign. It can be done. We did some simulation based work, but it's complicated, so I'm not going to go through this because there are delays in the chiller. The chillers are constant speed, they're not variable speed. But their power consumption changes depending on how much cooling you're asking from them. And these models are complicated. Nobody even knows very well how to model these things. So I think recently we kind of got back to this problem. This is again a kind of research frontier. Nobody actually has figured out how to do this. But there's a lot more capacity in this time scale. In fact, this is more valuable. 10 minutes up and down, fine, frequency regulation. There are a lot of papers on frequency regulation because some people believe there's money to be made. And in fact, there is some money to be made. But if you're talking about this future scenario with lots of renewables, what we really need, as we use more and more renewables in the grid, what we need is more and more long-term storage, right? 2 hours, 4 hours, 6 hours daily. In Europe, the goal is now seasonal energy storage. Of course, none of this is going to work for seasonal. It's not going to even work for a week, right? But the longer you can make it, the more valuable it becomes. And chillers can be really useful for longer, a few hours easily. I don't know how many hours, maybe 12. I'm reluctant to say this can be done for 12, but 6, I think we can do. So we did some simulation studies, but haven't done experiments yet. Okay, summary is commercial HVAC systems have large flexibility in power consumption. Not just commercial, residential too, but commercial is what I talked about. So flexible load plus intelligent gives you virtual energy storage at low cost. So ultimately reduce the cost of renewable integration. That's the final goal. The extremely important point is that every load has a particular time scale at which you can extract this energy storage service. You have to respect that time scale. Everybody knows that there's a limit in amplitude, but the fact that there's a limit in time scale, that's not very well appreciated. Especially if you go to industry, you have to always fight against them. They kind of understand intuitively, yeah, there will be a limit, but they don't think about it carefully enough. So this is really important. So moment somebody says, oh, let's vary demand to do this, you have to, okay, wait, what kind of demand? What is the time scale of flexibility, right? If you do more than that, then it's going to violate consumers' quality of service. That's going to lead to consumer backlash, and that's going to be worse than not doing anything at all, right? Lots of research questions you guys can work on. All right, thank you. Any questions? No? All right, good.
That's awesome.
I can turn the mic off?
Yes.
Okay.